Hello, I'm Dongmin, and along with Charlie, Akil, and Thomas, this is our 1-to-1 statics home experiment assignment. The two experiments we will be going through is a friction experiment and a moments experiment. For our first experiment, we decided to find the amount of force that is required to push a 362-gram wooden block up a wooden plank which is at an angle of 21.8 degrees. In order to find this force, we first had to find the angle at which the wooden block begins to slide. As shown in the video, we found out that the wooden block begins to slide at an angle of 29.1 degrees, which was measured with the help of a phone application that can measure angles. After finding the angle, we made some calculations in order to find the coefficient of friction of the wooden plank and block. The free body diagram of the wooden block shows us the forces acting on it which are at an angle. However, we can use a rotated coordinate system in order to make all the forces act in a horizontal or vertical direction. Since the wooden block is in static equilibrium, the sum of the forces in the horizontal direction and vertical direction are equal to 0. The forces acting in the horizontal direction is the friction force acting in the positive direction and the horizontal component of the weight force, which acts in the negative direction. Therefore, making the friction force and the horizontal component of the weight force, which is W1 sine theta, equal as shown in the calculations. While the forces acting in the vertical direction is the normal force exerted by the wooden plank onto the wooden block, which acts upwards, and the vertical component of the weight force, which acts downwards. Therefore, making the normal force and the vertical component of the weight force, which is W1 cos theta, equal. We then use the equation F equals mu n, which is the friction equation, in order to find the coefficient of friction by rearranging the equation as shown. Since F equals to W1 sine theta, and n is equal to W1 cos theta, and mu is equal to F over n, we can use trig identities to make mu equal to tan theta. Therefore, by substituting in 29.1 degrees into the equation, we can find the coefficient of friction, which is 0.557. Now that we have found the coefficient of friction, we can find the minimum force that is required to push the 362-gram wooden block up the plank at an angle of 21.8 degrees. The video shows us the block being pushed up the wooden plank at an angle of 21.8 degrees. The mass of the block is 362 grams, and so the weight of the block is 3.55 newtons. The free body diagram of the wooden block shows us the horizontal force P, which is the force that is required to push the block up the plank, and the other forces acting on the wooden block. Again, we use rotated coordinate system and break the weight force and force P into its horizontal and vertical components. Using the sum of forces equal to 0, we are able to find P. First, we find the normal force by using sum of forces in the vertical direction is equal to 0. Therefore, n plus P sine 21.8 degrees minus 3.55 cos 21.8 degrees is equal to 0. Thus, rearranging for n, making n equal to 3.3 minus P sine 21.8 degrees. Then we use the forces in the horizontal direction is equal to 0, which gets us P cos 21.8 degrees minus 3.55 sine 21.8 degrees minus the friction force. The friction force is equal to the coefficient of friction, which we found earlier, multiplied by n, which we calculated just before. Therefore, we can rearrange to factorize P out. Then we make P equal to 3.15 over cos 21.8 degrees plus 0.557 sine 21.8 degrees, which equals to 2.78 newtons. Therefore, we can conclude that the horizontal force required to push a wooden block of 362 grams up a wooden plank at an angle of 21.8 degrees is 2.78 newtons. For our second experiment, we decided to see how the distance of the blocks along the plank affect the readings on the scale. So, we decided to use two blocks with a weight of 362 grams and 317 grams placed at three different sets of distances along a 1.2 meter long plank, and recorded the vertical forces on the right side of the plank using a scale. The video being played shows the two wooden blocks being placed at different sets of distances of the plank. The right side of the plank is point B and is where the scale is, and the left side is point A, which we use for our reference points for the sets of distances. We first placed the 362 gram block 0.7 meters and 317 gram block 0.5 meters from point A and recorded the scale reading. Then we put the 362 gram block 0.5 meters and 317 gram block 0.3 meters away from A and recorded the scale reading. Lastly, we put the 362 gram block 0.9 meters and 317 gram 0.7 meters away from A and recorded the scale reading. Here, we drew a free body diagram of the plank showing the forces acting on it. The first set of distance we used for the blocks showed a scale reading of 1.317 kilograms, and thus the experimental value of the vertical reaction at B is 12.9 newtons. The second set of distances measured 1.268 kilograms with a vertical reaction of 12.4 newtons at B, and the third set measured 1.354 kilograms with a vertical reaction of 13.3 newtons at B. Thus, since we all know the forces except the vertical reaction at A, we can use the sum of vertical forces is equal to 0 to find the vertical reaction force. In order to find out how accurate our experimental values were, we decided to also calculate the theoretical value and compare them to calculate the percent error. As shown in the slide, in order to find the theoretical reaction forces of B and A, we used moments at a point is equal to 0. For VB, we took moments at A, and for VA, we took moments at B. Therefore, finding out the theoretical values for VB, which is 13.4 newtons, and VA, which is 13.5 newtons, for the first run. In order to find the percent error for both A and B vertical reactions, we took the positive difference between the experimental value and theoretical value and divided it by the theoretical value. Then times it by 100 to find the percent error. For the first run, we found out that the percent error for VA was 9.68% and VB was 8.28%. We then repeated this process in order to find the percent error for run 2 and 3, and we calculated that the percent errors for VA is 1.37% and 9.68% respectively, while the percent errors for VB is 0.813% and 8.28%. Some reasons why these errors may have occurred may be due to not placing the blocks at the exact distances as we stated. The mass of the block might not have been exactly 2.06 kilograms either. The scale's display was often unstable and fluctuated a lot, and the rail and scale may not have been supporting the beam at the exact ends of the beam. However, some of the values were still relatively close to the theoretical value, despite the percent errors. Through our experiment, we came to a conclusion that the further away the blocks were placed from point A, the greater the moment around point A, causing there to be a greater vertical reaction force at point B. Thank you for watching our 1-to-1 static swim experiment assignment. Hope you enjoyed.